this is what we're dealing with. Now, I need y'all to help remind me of something. Didn't we finish going through the syllabus? Yes?
Yes.
Okay. And didn't we finish going through research paper instructions? Yes. Did I go over my locator card when I'm in class, when I'm not?
Yes, sir.
Yeah, I thought we did that too. Okay. But we didn't get to do anything on safety, right? Right. That's where we're going to start today. So I'll try to do it fast because we've already lost another week. Okay. This is terrible. Okay. Monday was a holiday. Wednesday was a snow day. Okay. Which really didn't turn out much of a snow day, but maybe some places it was. So we're going to first talk safety, and then we'll start this slide, which is actually where calculus begins. But for those who are new, how do you access the things we just talked about? Okay? Well, are both of you familiar with Blackboard? Okay, good. In Blackboard, you know, when you get in the course, then the upper left corner, at least it is on the instructor side, I assume it's the same on the student side, there's a series of blue tabs it is for us, okay? And in those tabs, about the second, third, or fourth one down, somewhere there, it says content. If you click on content, then you're going to see a whole pile of stuff show up. The very first thing is syllabus. And even for those who were here last time, there have been some minor changes to the syllabus because the administration decided during our meetings at the first of the term, most of us already been working on our syllabi, that we needed to change formats. So that meant we had to redo stuff. Okay? And I think probably what I showed you was mostly the old format. Can I get your name, please?
Diamond Roberts.
Okay. And you go by Diamond?
Yes, sir.
Okay. So you're another new one in the class, right?
Yes, sir.
All right. Welcome. Okay. Good deal. So I was just explaining where to go to find things on Blackboard. When you go to the home page for this course, upper left corner is a series of tabs. Like the second or third one on the instructor side anyway is one that says content. And when you go to content, you'll see the syllabus. Okay? And like I was saying before, I have made some changes to that because I was just saying this. During our meetings at the first of the term, they said, oh, you need to change your format and get all this stuff done. And we asked where it is. Oh, it's blah, blah, blah. It's on the L drive. So I went to the L drive. Nothing was there. So I continued, but I thought I knew what they were talking about, so I got it updated some. And that's probably what you saw, a little bit of the update. And then, after we had all done those syllabus again, they said, no, you got to add some paragraphs too. So that's probably the new stuff that we didn't go over in class last time. So if you go to the YouTube video, and I'll get to that in a minute, you'll see me talking about one syllabus that's not quite like the syllabus that is in Blackboard now. The one in Blackboard now is the correct one. So go through that. If you have any questions, ask me. Okay? I even found an error this morning, so I corrected that and reloaded that and then they had some terrible formatting stuff, so I got that cleaned up some too. So anyway, that's the syllabus. The next thing is the research paper instructions. That we did go over in class the first day, and that is the same in class and what you see on Blackboard. Okay? So if you go to the YouTube video, you'll see the same thing being talked about. So that's the second thing. The third is my locator card. That's where I am when I come to campus, when I leave campus, when I'm in class, when I'm not in class, when my office hours are, that kind of stuff. That's all out there under locator card. And I think the next things are the PowerPoints. Okay? Every section that we possibly may cover has its own PowerPoint show, and each one of those is out there under content. Okay? When you get through all those, there's a passel of them, okay? Then there's a bunch of several websites that either students have found and told me about and said they found useful for the course, or I found and I thought, well, they may be useful. Okay, so I put those websites out there. So if you need any additional help, there's that there. Let me say this about one of them. One of them is name of it is Slader, S-L-A-D-E-R, and that's based on the text. The trouble is, this is a new edition of the text, and Slader didn't have the new edition, so I loaded the old edition. And frankly, hardly anything changes when they change editions that I've ever been able to tell. The reason they change editions about every 3 or 4 years is the publishers only make money selling new books. Used books they don't make any money on. So therefore, once the book has been there 2 or 3 years, a lot of used books are out there and the publisher's not making anything. He has the authors have to do a new edition with hardly any change, maybe change colors, change little things like this, and then they sell you new books again. Okay? It's a racket, and I hate it, and I feel complicit in it, but I have no control over it. Sorry. Okay, so anyway, Slader has the older edition, but like I say, I don't think you'll find much change. If they have page numbers, the page numbers will probably change, but that's about it. There will be occasionally probably a few other things. All right. And then, the last thing I think listed there is Math 125 YouTube videos. Okay, so that very last thing under content, you can go to that and you can see everything we talked about in class last time. Okay, and if you're late enough looking at it, you may see everything, and then the next one. And by the way, and here's how I do it. I load those, they're recording now, and at the end of class, I'll end the recording and send it to YouTube. But it takes a while to get there, okay? So sometime, usually later this morning, that morning, I will be able to upload it to YouTube and put it in the playlist. And what you see on that thing in content, the link there is to my playlist. Now, here's the thing about that. I've taught this class before, probably several times, okay? Many times, but so what you'll see in there is a bunch of files. When you go to the playlist, you'll see a bunch of files. This term's files are at the very bottom. So when you see the syllabus at the bottom, that's this term. All the ones before this was previous terms. Previous terms, we used a different book. So the slides won't look the same. You won't see anything pretty and colored and things like this. That last book we had terrible slides. Okay, awful. Okay, almost hard to teach from, but I managed to do it. But the material is pretty much the same, maybe not in the same order. So they may not be useful to you, or they might be. Okay, so it's up to you. But go to the bottom, because they always load to the bottom. And that's where, and as I recover new material, then I'll take off the older ones. So there'll always be something out there you can refer to. Okay. That's in case the system goes down or something like that. There'll be something. I may not be able to record one day, so I'll work on the board. There won't be anything on YouTube, but you can maybe follow the same type of stuff in the previous classes. Though it's going to be more difficult with a different book. Okay, so that gets us up to that. Now let me say this other thing. I may have said it before for those who are here, but for those who are not. This book, this author, Ron Larson, also Bruce Edwards, he co-wrote this one. But Ron Larson offers the best student resources of any author I've ever taught. Don't like the publisher. I think they overcharge. I don't like Cengage, but he is a great author. Notice on the very cover, it says with CalcChat.com. Well, it doesn't say .com, but it is. And with CalcView. These are websites. Every odd number exercise in the text is in CalcChat.com. Okay? So I'm going to assign the odd numbers because 2 reasons. Number 1, answers to odd numbers are in the back. So therefore you can do the homework exercises, check your answer. If you can't get it, see if you can figure it out. You can't possibly figure it out, go to CalcChat.com. And there it'll be worked out for you, and you can see what it is. If you still don't understand why, ask me in class. Now, selected things are under CalcView.com. Okay? Those will be designated by the red exercises. You know, the numbers 1, 2, 3, 4, 5. The odd numbers that are in red, those are on CalcView.com. That's actually a tutorial and more information than just working out the solution for you. Okay, not just that. I think I'll wait for the last part until we get there, so I'll show you. Any of you have books so far? A few of you do. Okay? I would say get the book because I think you'll find it really, really useful. Again, because of this. Now, one other thing that was not here last time. Can I get your name, please? Tyler. Tyler, okay. All right. My hearing's bad, by the way. If I ask you things over and over, it's because I don't hear well. And that's why I talk so loud, probably. I don't think I'm talking loud, but everybody else knows I'm talking loud. Sorry about that. Okay, one other thing that's changed since the last time we met. Somebody, I think in this class, but if not in this class, in one of my other classes that uses Cengage books, and I'm teaching 2 other courses that use it, someone asked for WebAssign. If you bought the new book, you got a code for the course, and you can't use it unless I give you a code. Well, I sent an email. I put it as an announcement on Blackboard and sent an email, and all of you should have that code. If you don't have the new text, you can't use it, you know, that's fine. I'm never going to make an assignment on it, but it does have tutorial help and more practice problems. So use it, okay? If you got it, use it if you need it, okay? For those who don't have it, you don't have to buy it because I'm not going to ever make an assignment with all these other extracurricular materials that this book provides and this author provides. I see no point in it, but it does have great tutoring, you know, and help on things. Here's one reason I wouldn't make assignments on it in the first place, and we'll run into this repeatedly. Maybe not so much early on, but later on, big time. Especially in calculus, but in any math. There's usually more than one way to express an answer. You could have 1/2 x squared minus 3, okay? Or you could write that as x squared minus 3 over 2. Same answer, okay? Or you could write it as x over 2 minus 3 over 2. Same answer. Absolutely correct answer. All of those computerized packages are only looking for one answer because computers don't know how to work problems. They just feed what someone's fed in. I mean, that's all they do. Okay? So someone fed in one answer, and if you don't get that answer, it says you're wrong. Okay? And then you get frustrated, and you think you did it wrong. You try to find out how didn't do it. You didn't do it wrong. You did it absolutely right. They're just looking for a different form. Boy, when you get to calculus, it's not just 3 different ways to express an answer. There's tons of different ways to do it. So that's why I don't use it for homework and things like this. But it is a useful tool, has lots of tutorial help and things like this. Use it on your own and get frustrated on your own. But if it frustrates you, ask me and I'll say, no, that's the correct answer. They're just looking for a different one. So don't let it frustrate you, okay? I'm not going to be grading that because I found out I had to wind up regrading lots of things because the system said a right answer was a wrong answer. All right. Any questions on the course? Okay. Yes.
On the research paper,
yeah.
You just have to pick one subject.
Yeah, you pick a topic, any topic that you'd like. It can be a person. It can be a event, application. I really like the application problems. Anything like that, and then you have to go outside the book. Now the book has some good things. This book is better than the last one. Was about providing historical perspectives and things like this. You'll see them all over here. If you see something that's interesting to you, okay, you can write your paper on that. However, the book is not your source. It's the source of the idea, but your sources for your paper have to come from a library or internet if it's a reliable source on the internet, okay? There's a lot of garbage on the internet, so don't, listen to the YouTube video from the first class. I talk all about that research paper. Yeah. Good question, though. All right, safety now. I'll try to go through this quickly, though I don't do anything quickly. Sorry about that. 3 areas of safety we want to deal with, okay, to have you thinking about in case anything happens. You don't say, what do we do? Yeah, that's what I say. Okay, let me see. We talked about what to do. Where do we go? Okay. I'll usually take a lot more time and get y'all a lot more involved. I'm just going to go through it fast now. First of these, we'll talk about weather emergency or anything external to the college is emergency. You hear that siren goes off. It may happen on Wednesdays in this class because they do a test of it on Wednesday the 11th, and we'll be in class then. So don't get up and run then. But Monday or any time other than the time, or if it looks like it could be severe weather, then what do we do for weather? For weather, think 2 things. Low, interior. Okay? Low and interior. So where do we go? We go out the door right here. Now, when I get this far from my microphone's in the computer, so it's probably not going to pick me up too well. But you go, here's a map of where we are in this corner classroom here. Go out to the hall, hang a left, go down that half flight of stairs right there. Immediately at the bottom, hang another left, go down a full flight of stairs. Now you're close to as low as you can possibly go in this building. There is a few more little steps there, but you're coming out on some decent places to be. For a weather emergency, the thing, like I said, low, get down to the lower floor, interior. Don't go anything on the outside of the building. This room would be terrible to be in. Glass. Trees, tornado can throw limbs through the window, shattering glass, cutting people. Get out of this room, low and interior. Now, when you go down, the first floor doesn't look exactly like this, but it's similar. This is the second floor. When you get down those stairs, immediately in front of you are the restrooms. Now, those are really safe areas. So, interior, the walls are close together. That's the other thing you think of, close together, and even better than that, corners. Corners are the greatest strengths of the building. A flat wall like this is strong. A corner is strong because now you've got 2 dimensions that are being supported. Okay? So low and interior, close walls, lots of corners. That would be ideal. However, a couple of negative things about a restroom. You might not want to spend a couple of hours there. Okay? And number 2, if we really did have a weather emergency, as in tornado or something like that, even straight line wind, severe thunderstorm, very likely we will lose power. If you lose power, the restrooms do not have emergency lighting. So now you're stuck in the restroom, not stuck there, you can get out, but you're in the restroom in the absolute pitch dark. Okay, so again, maybe not the most pleasant place to be for an hour or 2 or however long it takes. So, next to the restrooms, there's actually a couple of more steps going down, and then the next room on the right is not the corridor, but underneath that corridor, this is the second floor, is the academic dean's office. And again, that's a small space, closed walls, lots of corners. Most of the time it's locked up because the academic dean most of the time is on the Birmingham campus. But if it happens to be that she's there, or the assistant academic dean, if he's there, or occasionally they'll let other instructors from the Birmingham campus use that office when they're over here and they don't have a place to go to. If someone's in there and they invite you in, you can use that. Again, closed walls, corners, but no emergency lighting, but a little more pleasant than the restrooms. Okay. Next to that is a classroom. It's room 160. If any of you did developmental math here, you may be familiar with that classroom. It's a big room. Now, the back wall of that room is a very solid wall. Behind that is soil. There's not another part of the building there. It's the soil. It was dug down. That is the lowest level. So there is a very strong wall. The corners, again, are strong. Out in the middle, if there was a crashing happening above, it could come through the ceiling. So stay away from the middle of the room. But it's a big, spacious area. Along the walls, in the corners, especially that back wall, very safe. Okay? Next to that, you have to go through the glass doors that are the library. Now be careful here. Go into the library. The first door on the right in the library is a computer room. And again, that's pretty smaller space than the classroom. Closer walls. That back wall, again, very safe. That back wall is against, the soil. So very strong wall, and the corners are very strong. So that's not a bad space. Next to that is what I call the reference room or the research room or something like that in the library. It has the atlases and the globes and that kind of stuff. You don't check out books from there, you can just use them as reference. Not a bad space either, especially that back wall is the safest. The corners are good. The only thing sort of negative about that is a little bit bigger space in the computer room, but it does have shelving. So if there is shaking of the building and stuff, some of the shelves could come down. The back wall, not likely. The other walls, it could happen, so that might not be the best. Don't go any further in the library because then you're in the external spaces where there are windows. Don't go any further. Actually, one of the better places, it isn't perfect, is that hallway. Here are the advantages of the hallway. The walls are closer together than the classrooms, but there's no corners. That's the disadvantage. But the other advantage is the hallway does have emergency lighting. So sitting along one of those walls, not bad. That is a pretty safe area. You'll have lighting. You'll be able to talk with friends, that kind of stuff. You won't be in the dark. So that would be the best place to go. Now, let's talk about how we get there. If you hear that alarm go off, here's a couple of things on it. Number one, you go orderly. Don't rush. Don't panic. That usually gives you plenty of time. Now, all of you look really able-bodied right now. I didn't see any of you limping in, no crutches, no wheelchairs. But if you go take a holiday weekend somewhere and sprain an ankle, break a leg, injure yourself, I'm going to be going with you, the injured party. I'm going to get you down the stairs. There are no elevators in this building, so there's not really a good way to get there from here, so I'll be helping. And it may be I might ask some of you other fairly able-bodied looking characters to help me if I need help getting that person down. So the odds are I'll be the last one out of the room, the last one down there to this area. What I will also carry with me is the grade book, the roll book. Because when I get down there, I have to call the roll again to make sure everybody made it. Because I can't be with the front. I'll be at the end. I won't see everybody. So hang together, stay together, and I will then check and make sure you're there. What not to do? Oh, man, I need to get home. My dog's outside. I need to let her in. No, you don't. The road is about the worst place you can be in severe weather. Don't go out into it, okay? So don't be trying to escape, get away, get home, no matter how crushing the situation is. I had the only time I can recall that siren going off, and this had to be 15 years ago or longer. I was teaching in this room. It was late in the evening. It was a 5:30 class, and one guy, he was really worried about his girlfriend getting home. This was about the time she was going to be on the road. I said, look, not going to do her any good if you get killed in the car. So she'll probably be safe. There's nothing you can do about it. Relax, And, fortunately, everything moved north of us. There wasn't really a bad situation. That's the one that hit Oak Grove. Any of you are familiar with that one? That was, about 15, 20 years ago? Yeah. Yeah. What's that?
98.
98, okay. Long time past. Closer to 20 years, 19 years ago. Okay. So, don't, goodness gracious, money all over the place here. So don't leave. I'll go down, call roll. Once I call roll, if then you want to move around, mingle with friends, that's fine. Stay inside though until we hear they'll give us all clear. So that's weather. Another type of emergency we have to always keep in mind is something inside the building that's a hazard, as in fire, chemical spill, or something like that. Okay, now let's start with the worst case scenario for us. What if, say, my computer just blows up, catches on fire, and starts burning the papers around it? What do we do? What are the things you need to think about doing? Okay, leave. Did I hear leave? We definitely will be leaving the classroom. And we leave the room, we get our safety and let the room burn and all the people around us get burned up. No, we don't want to do that, do we? So the two things to think of if the event starts here. If we're the first to know, smoke starts coming out of the ventilation system. If we're the first one to know that, two things we do before we leave. Somebody, in fact several of you, now the best number is actually campus police. And this was one given to me by Lieutenant Tate. He wrote it down. This is his handwriting. 426-3654. That is the number for, this is what he told me, the unit that the duty person has on his or her body all the time. 426-3654. If you can program that into your cell phone, good thing to do. Now, if you don't get anyone there, if you don't have that programmed in, or get where it is, next best is 911. If it initiates here, we need to let someone know. Now that gets the ball rolling for the building. How about the people in the building? What else do we need to do? If we're the first to witness the fire, evidence of the fire. Fire alarm. Where is the closest fire alarm to us? Right here? Anyone know? Okay, speed things along. Nowhere on any of these halls, these old hallways here that you see the terrazzo floors and the tile walls, that kind of stuff, not a single one of them. This building was built before fire alarms were required in the code. So nothing in the old part of the building has a fire alarm. Nothing, nowhere. Don't go wandering down these halls. Here's where you do go. I would suggest two people go. That way, if one falls, you got a buddy system. Go out the door, hang a left, go down that half flight of stairs. This time, go to that corridor that goes across. That corridor goes across to, now, the reason there's nothing here, there's no second floor. That's now, this level is second floor. You go through that corridor, you haven't gone up or down a single step, but you're on the first floor now. That's the newest part of the building right there. And as soon as you come out into that hallway there, you're in the newest part. They do have fire alarms there. If you hang a left, there's one on the wall right there. If you hang a right, there's one on the wall right there. Just look for the fire alarm, go and pull it. Okay? You've always wanted to, haven't you? Yeah, what would that be cool? But let's hope you don't ever have to. Okay, so the first thing, 911, simultaneously someone's going down to pull the fire alarm, and the rest of us are exiting we're exiting the building. And where do we go? Just like before, out the door, hang a left, go down this half flight of stairs, hang another left, go down the full flight, then you go out, not in. In for weather, out for fire or building emergency. Now where do we go there? Used to be, I'd say, 75 feet, 25 yards out into the grassy area. That's where they used to say. Now they say go into the parking lot down there. So go into the parking lot down there, between this and the Ethel Hall building. Go into the parking lot and stay together. Because again, I'm going to be the last one out, making sure everybody made it out. We may have somebody pulling an alarm somewhere. They've got to catch us. And by the way, this is our closest exit. That one right there, when you go down that full flight of stairs out of the building, that's the closest exit to where we are. Now, I hate to tell on ourselves, but the last time we had a fire alarm, which was a couple of years ago, a fire drill, I'll say that, fire drill. I don't know who came up with this idea. I objected at the time. I did it my way, and I complained to them afterwards. I think they've changed it. When you do a fire drill, you're supposed to do what you would do in case of a fire. What they said to do that time, They said, everybody go out the back doors. No, that's not what you do in a fire, because then you've got a bottleneck right there and people can get trampled. No, you don't do this. You go out the door you're supposed to. And when I took the class out, I said, that's where we would go in case of a fire. Now let's go to the back parking lot where they want us to meet and debrief. So I said, no. I actually had other instructions. No, we're supposed to go out of this door. I said, no, you're not supposed to. That's wrong behavior. You don't practice wrong behavior in a fire drill. You practice right behavior. So I took them out, and then we went up the side of the building, which was wrong, but I said, that's where we go. Here's where we're going to go today. Okay? I was real stubborn about it. I think they changed. Well, they haven't had a fire drill since. Put it that way. So that's where we go. So in case it doesn't start here, the first time we hear is a fire alarm. That's what we do. And I'm the last one out. And I don't want any of you to say, hey, the building's on fire, no more classes, I'm out of here. Don't do that. Because I'm going down with my roll book, and when we all get together again, I call roll, and if someone's not there, someone else has to go back into the burning building, the chemical spill building, whatever is going on, risk his or her life or health trying to find the person who drove off because of the boat. No more classes today. So stay together. Same thing true with the fire thing. If I can't find you down there, I or someone else has to come back into the dangerous areas of the building where the weather's happening and look for you. So always stay together until we call roll and we get word, okay, we are going to cancel classes there. Okay, we're now going to move here. Or okay, it was a minor thing. You can go back to your classes. Yeah. Wait until we hear official word. That's fire or chemical spill. That's weather. One other, and we didn't ever. I never even thought about this, but nowadays we have to think about it. Active shooting. Sorry about this, folks. Okay, what do we do in case? Now, guess what? I'm hard of hearing. If some of you hear something pop, pop that sounds like it could be gunfire, you let me know, okay? I'm going to be up here talking away as you let me know. And we don't risk it, okay? What do we do? What I do, I have a key for this door. Now, this door cannot be locked from the inside. There's no key in here. There's no buttons on the edge. I have to physically go outside, fumble through my keys, get the right one, lock the door, don't pull it to. I come back in, and we do that. The trouble with this room is there's another entrance through here. And here. And there. Okay.
So you have like all the doors?
Okay. Now here's what I do here. I don't have a key to that hallway door out there. So what I'll do is go and close that door. But then I come back. Now, this one does have a button on the edge. So I can press that and it locks from the inside, but not from the outside. So we're stuck in. He can't, I'm saying he can come right in. So this is not the door to lock. Now this door has a deadbolt. I don't have a key for that. However, this one I don't have a key for, but it has a button on here. This one is locked on the outside, not from the inside. So this is locked. Okay?
What did he shoot out the window?
Okay.
What did he shoot out the window?
Okay, I'm getting to that. So what I do, and I'll try to do it, but if y'all can beat me to it, because I may be fiddling with that door, go and close that hallway door, come back in, lock that door, and like you said, there's a window. You can see, okay? So we have this door closed, but you then close this door. We can't lock it, but now he can't see in, right? And guess what? We're going to close this door. We won't lock it, but we'll close it, okay? All right, we'll get the math. So watch YouTube video. You'll get what we do that.
Okay.
Now, the rest of us, back here. He can look in through this window, so we don't want to be visible here. We turn off the light. We're very quiet. We're all back here in the corner. He can even fire a weapon through the wood. I don't know if this is solid door or veneer or what. He could fire a thing through this. You don't want to be on this side. It's hard to go through concrete block. So we're all back over here, as quiet as we can be. Try to keep your prayers silent. No, okay. All right. And we stay there until we hear an all clear from someone official. Police, they have keys. They can let us, come in and say, anyone here? I'll look around. Okay, so that's the thing. Be very careful. Think this. Think it ahead of time so at the time it's happening, if it hopefully never happens, but if it did, we don't do something stupid, that we get everything that we can cover. All right, any questions on any of that? Good deal. Sorry. That's safety. All right. Calculus. What do you think of when you think calculus? Anything? It's probably the first time you've taken it. You've had pre-calculus. How is calculus different from pre-calculus? Anyone know? Okay, you think about what? Excellent. That's one of the first things we're going to do in calculus. Okay? But before we do that, we have this chapter on limits. And to me, limits are gaggy, but they explain what you're doing when you're getting that slope of a curve. So yeah, we're going to start with limit so we can talk about slopes of curves. Okay, so this is a preview. Now, by the way, I probably said this before, but let me say it again. There is a chapter before chapter 1. It's not chapter 0, it's chapter P. Preparation for calculus. Okay, not preview, preview. It's preparation. Chapter P. Graphs and models, linear models and rates of change, functions in their graphs, review of trigonometric functions. Hopefully you all had that before, right? The first part is mostly Cal 1, pre-calculus algebra. The last part is pre-calculus trig. If you need to, go back and review that when you get your text. If you have any questions, things that you're fuzzy about, oh man, I don't even remember if we did that, or oh, I remember we did it, but I don't remember how we did it. If you have any questions on that, bring them to class next time. Okay? Now we're going to do a preview of calculus. Okay? And again, like I said before, this book has far better videos, slide set, PowerPoints, than the others. So if you do go and look at those others, you'll be as disgusted as I was when I had to teach from them for years. But we went to this new book, actually last fall, but I didn't teach Cal 1 in the fall. I was taught 2 and 3, and we were still using the old book for that because those people already had it. Now, did I see someone with a different book? Have you got the same book? You got it, okay. Did I see someone with a different book? If you've taken calculus somewhere before, either here or somewhere else, and you have a calculus text already, really there's not much difference between the texts. I hate to tell you that. Calculus is calculus. It's just how you present it's a little different. So if someone does have a previous edition, an earlier version of something else, you can probably still use it. That's up to you if you want what we're doing. But what we're going to do in this, the objectives in this section 1.1, understand what calculus is and how it compares with pre-calculus. Just what I was asking. Understand that the tangent line, what you were talking about, is basic to calculus. Whether you know that's what you're talking about or not, that's what you mean. And understand that the area problem is also basic to calculus. Now that's actually getting into integral calculus. This is differential calculus, that's integral, and we'll talk a little bit about the difference of that. We're going to do integral calculus right at the end of the course, okay? Now, as I've already said, we have already lost effectively a week and a half. This is only our second class meeting, and we're almost in the third week of class, okay? So we are already behind. I don't like to rush things because if you rush things, you lose things, you miss things. Far better, I think, to get the basics down, and then anything you miss, you can build on it to get it. If you are rushing through the basics, you don't understand those, what have you got to build on? Sand, and it won't work. So let's go. What is calculus then? Okay? It's the mathematics of change. Now I'm going to mention a few folks here. These are potential paper topics as well. I don't know if I have this totally right, but this is the way I understand it. There was a guy, I always go blank on his name, who was studying planetary motion. And, there had been the big upheaval. At first, people thought the Earth was the center of the universe, and everything revolved around the Earth. The sun goes up and down, the moon goes up and down, the planets, the stars, they seem to go around the Earth. We're the center of the world, right? Like a teenager, right? No, I'm not. We won't say that. Okay? But when they were studying, stars and the sun followed pretty regular patterns. The moon followed a regular pattern, but it was different from the stars and sun. And then the planets, goodness gracious, they would sort of follow a pattern and then change and back up. And if you looked at them night after night and thought, what are those doing? In fact, that's what the word planet comes from, wanderer. Because they sort of wandered across the sky, whereas everybody else went in pretty close pattern. Why am I going blank on this name? I don't know. But anyway, this guy, along came Copernicus, who said, hey, this Earth is not the center of the universe. It's not even the center of our solar system. The sun's the center of the solar system. And then once he did that, the motions made sense. Once you understood the Earth is spinning. See, they never understood it. It doesn't feel like we're spinning, does it? But that's why everything else seemed to move around us, because we were spinning. They were fixed, we were spinning. Okay? But those planets, okay, they were the problem. And laws of planet, Johannes Kepler, okay, came up with the laws of planetary motion, and man, nothing had fit as well as that did. Okay? He came up mathematically that the sun is one of the foci for every planet, and every planet goes an elliptical path. Sorry. Okay. Sorry. I have to make sure y'all are awake. Okay. Never mind. And then he had rules about the things. Boy, that guy was good. He found out the patterns. Well, what he couldn't say, why did these patterns happen? What was the law of physics? We know gravity. We know, well, no, we didn't even know that at the time. Why were these laws working? He could tell us the laws seemed to fit the data, but not why it happened. So either he turned, or this guy, Isaac Newton, picked up the problem set. I'll try to figure that out. Well, with the math that was in his pockets, the tools in his tool belt, there's no way to do that. He had to deal with instantaneous change. Velocities, accelerations, and things like this. And the math at the time could only give you average changes, not instantaneous. So, can't do it. No, he said, let's just develop a whole new mathematics. Okay? Calculus was a brand new approach to, it incorporated everything else that had been done, but did things you never could do before. Okay? So therefore, this says calculus is the mathematics of velocities, not just average speed or average velocity, but instantaneous, constantly changing velocities, accelerations, which makes those velocities change. Tangent lines, okay? Never could figure the slope of a tangent line before because it only had one point, okay? And you need 2 points to get a slope of a line. So how would you get because a tangent line only touches a curve at one single point. So slopes in general, yeah, you could do average slope, good. Areas, okay, now I can do the area of this board. I get me a measure, do length times width, and come up with the area. But what if that was a curve up there, okay? How do I do the area of that? Why would you do a board like that? I don't know, but you could. And so areas of anything other than regular shapes, how do you do those? Volumes, that's even worse. I can do the volume of this room. Might be difficult with all these little corners and things in it, but you could do it. But what if we were inside a sphere? We know the volume of a sphere, but let's say we're inside a geometric shape, like a frustum of a cone or something like that. How do you do the volume inside that? Calculus allows us to do that. Arc lengths. I can measure the length of that thing, but how can I measure how far that curve on that P is? Well, if I had a flexible tape and I could tack it down at every point, I could come up with an estimate. That's not a very easy way to do it, okay? With calculus, yeah, you can do arc lengths, the length of any arc, if you know the function. Centroids, okay, that's the center of mass. For very simple shapes, maybe we could do it. Any odd, irregular shapes, need calculus. Curvature, you talk about curvature of a circle or a sphere, but for any other kind of shape, how to do it? Calculus. Variety of other concepts have enabled scientists, engineers, economists, just all sorts of areas to study nature, to study things that don't follow is just regular patterns, okay? That's what calculus does for us. Although pre-calculus mathematics also deals with velocities, accelerations, tangent lines, slopes, and so on, there's a fundamental difference between pre-calculus mathematics and calculus, and that fundamental difference, the pre-calculus mathematics is more static, whereas calculus is dynamic. And basically, what the concept is that links the two is the concept of a limit. And that's why they did all this blah, blah, blah at the beginning. Okay? Here are some examples. An object traveling at a constant velocity can be analyzed with pre-calculus mathematics. Constant velocity meaning same speed in the same direction. Yeah, we can handle that. To analyze the velocity of an accelerating object, something that's changing speed, and then at any point it has a different speed, you've got to have calculus. Okay? The slope of a line can be analyzed with pre-calculus mathematics. You got 2 points on the line? Yeah, fine. To analyze the slope of a curve, however, exactly what you said, you got to have calculus. Okay? We'll get to it. The curvature of a circle is constant. Now, this looks like it's almost part of a circle, but it's not completely part of a circle, so that's not a circle. If we had a circle, yeah, you can talk about its curvature. 1 over the radius, by the way, is what that is. But if it's any other shape, you need calculus. The area of a rectangle. Yeah, we can figure out the area of this room, say, area of the board, say. To analyze the area under a general curve, you need calculus. Okay? Now, in your book, you have figures that illustrate this. I thought they would show up on, again, it's my first time teaching with the slide set. So each of these situations involves the same general strategy. The reformulation of pre-calculus mathematics through the use of the limit. That's the thing that ties the two together. It extends pre-calculus and gets us into calculus. So one way to answer the question, what is calculus? It's I've never heard this one before, say that calculus is a limit machine that involves 3 stages. Okay? The first stage of this machine, this limit machine, is the pre-calculus mathematics, such as the slope of a line, the area of a rectangle. We'll get to see this maybe even today, if possible. Second stage is then the limit process that links us to what we need. And the third stage, the new calculus formulation, such as a derivative for slopes, integral for areas. So the pre-calculus area, mathematics deal with the first stage, the limit process is the middle stage, and then you get the new formulation from the third stage. Here's those slides, okay. Here are some familiar pre-calculus concepts coupled with the calculus counterparts. Okay. Pre-calculus algebra, the book that we use said the algebra of functions. Okay? So let's say this curve represents, that's the graph of some function, y is equal to f of x. So for any value y here, it depends on where your x is, that calculates your y. Okay? For any x is 1 and only 1 y. That's what makes a function. So therefore, in pre-calculus algebra, if you know what the x is, x equals c, plug that into the function machine and find out what the y value is. Y is equal to f of c. that would be the y value corresponding to that x value. Because a function only has one y for any given x. Once you plug it in, you know what it is. But what if we had this curve that you knew the y value here was undefined? Well, I'm going to use that word now. I won't use it later. You can't figure this because, say, the denominator of this function form here had a x minus c in the denominator. Well, then x can't equal c because x minus c would be 0. And you can't have a denominator with a 0 in it. You can't do it, not in pre-calculus algebra or in any algebra. But with calculus, you can talk about the limit as x approaches c from the left, as x approaches c from the right. If those two limits are the same, yep, that's the limit of f of x as it approaches c. It may not have a value there, or the value may be something else. You may define it to be 0 or this or anywhere in between. But the limit is what it would go to if you went left or right. That's what limits do, that pre-calculus algebra. Because of that x minus c in the denominator, you can't do it in algebra, period. Now, the slope of this line here, yeah, if you know any 2 points, you know the difference in the y, the difference in the x, and that gives you the slope. Change of y and change of x. Hang on to that concept. We're going to use that over and over and over again. Okay? But what if we have slope of a curve? Okay? Well, on the curve, you can't, if you pick some y here, x here, y here, say the slope here, that's not quite the same because this is a curve, not a straight line. So how do you do that then? Well, what you're looking for is the slope of a tangent line. This is a change of y, there's a difference in y, dy and dx, not a delta y and delta x. Okay, and we'll talk about those two. Calculus does that, algebra cannot. Secant line to a curve, that's the same type of thing here. You can do this average slope, average change between x equal this value and x equal that value by doing the y here, the y there, the slope delta y or delta x, that gives you the slope of the secant line. And you can have this point, say, get closer and closer and closer to this point, but you can't let it be on top of it because then your delta x and your denominator, delta y over delta x, goes to 0. Can't do that. But you can do it in calculus. Slope of the tangent line, that's exactly the type of thing that you figured out how to do. Now, driving a car, you know that you're at time t equal a, you're here, time t equal b, you're there. If you know how far you traveled on your odometer, divide that by the time, you know your speed. The average rate of change, say your speed between those 2 points. Does that mean you were traveling at that speed the whole time? No. Okay, when I left home this morning, the first few feet of my trip, I was going backwards. Okay, I was back down the driveway. I turned in the street and I hit a stop sign. It had a turn and turn. You know, I was not going my average rate of speed that whole time. If I was, there'd have been blue lights all around me. Okay, wasn't doing that. I wasn't about to do that. Stopping and going, stoplights and stuff. Once I got on the interstate, I was going a lot better. Okay, but still there were trucks and traffic and things like this. So I never was going at one fixed speed for very long. But my average speed, how far I went from home to here, divided by the time it took, that's the average speed. The instantaneous speed, calculus can give it to us. Algebra cannot. It can give us an average speed, not an instantaneous speed. Now your speedometer comes close. That's a device that almost does what calculus does. And like I said before, we know what the curvature of a circle is. It's 1 over its radius. Well, what about a curvature of a line, of a curve? Curvature of a curve, okay? Well, what we do there is find what they call the occluded circle that has that same tangent line there. Then if we know the radius of that circle, we know the curvature of that line, because 1 over the radius of that circle will be the curvature of this curve, but you have to be able to calculate that. You can't do it with algebra. You can do it with calculus. Okay, the height of a curve when x equals c. We already sort of did that one. Okay, just plug in c, and you know what f of c is, f of x is. Plug in c for x, and you got the height. But what if you want to know what's the maximum height? Now, this is where things like economics and optimization theory and this kind of stuff comes from. What do I want to say? Hey, I don't want just what the height is here. I want to know what say this is my profit line. I want to know my maximum profit. That's what I'm gunning for. I don't want to be down here. I want to be up here. But I don't know where the x is here. Calculus can tell us that. Where are you going to reach that? Find that maximum in between A and B there. Okay? Tangent plane to a sphere, and I don't ever remember doing this in algebra, but supposedly you can. Yeah, you really can. But we never talked about tangent planes to spheres. But if you have just some general curve surface there, no way except calculus can you get the tangent plane of that surface. We're not going to do all these in this term, by the way. Don't panic. Direction of motion along the line. Yeah, if you're going in straight line motion, yeah, I can figure out what direction I'm going. But what if I'm moving in a curve like this? Right here I'm going this way, here I'm going that way, here I'm going this way. Constantly changing. Anything that's changing, calculus is going to be required to give you the direction at any point on that line. Okay? On this line, you're always going the same one. If I know what I started, that's what I am anytime. Okay, now we're getting into integral here. Area of a rectangle, like I already said, the area of the board. Just measure the length and width, multiply, and you got that. But what if you have a curve and you want to know the area under this curve? Now that could mean how many man-hours of labor it took to do that job. It could be how much resources it's going to take. I mean, it could be anything that you're doing. What is the work involved in moving from there to there? Those could be areas under a curve. Algebra can do this, it can't do that. Now, you can approximate it, but you can't know exactly without calculus. Work done by a constant force, so I'm pushing on the board here. You know, I'm not doing any work because I'm not moving it. But if I'm pushing on the chair, okay? If I'm pushing at a constant force, yeah, I can figure out force times displacement. That's going to give the work done. But what if I have a variable force? Not much, a lot, then not much again. That's a variable force. How much work do I do then? Well, calculus can do this. Algebra can do that. Algebra can't do that. Center of a rectangle, yeah, I can do that. Yeah, just find the intersection of the diagonals, that's fine. But what is about the centroid of a shape? Where is the center of mass for that? Okay? For a region that has an undefined boundary up here, or a variable boundary up here, you need calculus for that. Length of a line segment, yeah, I can get a measure, a ruler, and do that. I can't do a ruler and do this. That's the length of the line. We talked about that before, too. Okay, calculus required there. Okay, surface area of a cylinder. I know what that is. I can calculate that. I can say, well, it has two ends here, and those are both circles, right? I can give you the area of a circle. And then I can take this outer area, and I can cut it with sound effects, you know, go in here, lay it flat. That makes a rectangle. I can calculate that area, add it to the two ends. Yeah, I've got that. Good luck with this one. Okay, no, you're going to have calculus to do that. Mass of a solid of constant density, yeah, we can do that. Mass of a solid of variable density, say it's denser at the bottom and less dense at the top. How do I find out how much mass is in that then? Or side to side or anywhere. You have to have calculus for that. Volume of a rectangular solid, length times width times height, yeah, I can handle that one. But what if that has a curved surface? No, I can't. I need calculus for that. Now, sum of a finite number of terms, yeah, I can plug it in my calculator, can I? Okay. I can come up with that with just plain mathematics. Okay? The sum of an infinite number of terms, again, calculus required. And we're not going to do that in this course either. That'll be Cal 2. Most of this is Cal 2 if it's not Cal 1. All right, so let's go first to the tangent line problem, okay? The notion of a limit is fundamental to the study of calculus. Boy, it seems like we've said that before. The following brief descriptions of two classic problems in calculus, first the tangent line problem, then the area problem, should give you an idea of the way limits are used in calculus. Okay? So let's start with the tangent line problem. You're given a function f. Here's the graph of that f. But let's just imagine you knew what that function was that has that for a graph. Okay? Now that looks like it's pretty close to a parabola. Maybe it is a parabola. We know the equation for a parabola. Basically, it looks like the vertex is probably somewhere around there. So you have a little bit of a horizontal offset and a little bit of a vertical offset. But we can figure out if that is a parabola. You could determine that. Okay. But whatever. Okay. That's the function. Given a function at point P on its graph that's not at the vertex, so has to find the equation of the tangent line to the graph at that point P. Okay. What do you need to give me an equation of a line? Two pieces of information. Okay, one would be what? Slope and a point. That would certainly give it to you. That would be called the point-slope formula. Now, if that point happened to be the y-intercept, then that would be the slope-intercept formula. Or if you knew 2 points, then you could do the 2-point formula. In other words, find the slope between the 2 points and then use one of the points in the point-slope formula. Yeah, you can come up with the equation of a line. But what if all you had is a single point? You know the coordinates of that point P. What's the slope of the tangent line? Algebra will not tell you that. Okay? Even if you know the function, okay, it won't tell you that. Calculus will. Okay? We don't have the tools yet, but it will do it. So that is the thing. Now, see what the next slide is. Yeah. Let's say this is that same curve. So except for cases involving a vertical tangent line, which not going to happen, okay? Because a vertical tangent line would indicate that the delta x is 0. You can't do that. So you never can do the slope of a vertical line. It's undefined, totally undefined. So except for vertical tangent lines, the problem of finding a tangent line at any point P is equivalent to finding the slope of the tangent line at P. Because once you know the slope, you have a point, you can do the point-slope formula. And you can do the equation of the line. Okay? But the thing is, how do you get that slope? Well, here's what they do. You can approximate the slope by using a line through the point of the tangent C, that same point that we had before, and a second point on the curve. Okay, now that's obviously not going to be the same as the slope here. But that's going to be a slope, right? Now let this point move, and then keep this one fixed. Let it move, and that secant line between the 2 points is coming closer and closer and closer to what the slope of the tangent line would be, isn't it? What's the problem, though? At any point here, you have a delta y. Okay, here's a delta y. Only here, okay, now, when I talked pre-calculus algebra, I repeatedly told my class this. I think Justin was in that one. I can't remember who else was in my pre-calculus algebra class. You probably were. What is f of x? The main thing to remember in pre-calculus algebra. What is f of x? Y. Exactly. If you remember y is equal to f of x, you got it now. So here is this is 1y. This is f of c. C, f of c. X, y. Y is f of x. C, f of c. That point is fixed here. Up here you have some other point. You've gone from this c, some delta x over here. So this is c, this is c plus delta x. Okay? That's this point right here. Then plug that into your function, f of c plus delta x. That gives you your y value up here, because y is f of x. Okay? But this is f of c here, so this difference in y's is f of c plus delta x minus f of c, and your change of x here is from C plus delta x minus C, which is just delta x, okay? So, you know the change of y over change of x, there's your slope, right? Slope of the secant line. And as you let this point come down, you just recalculate. So like when you do what your GPS tells you to do, recalculate, you're right. So you're doing that until you get down here very, very close. As long as you're not on top of that, you can always do the next slope. But once you get on top, your delta x goes to 0. And if that slope, if the slope is delta y over delta x. Now, here's the other thing. Now, this book doesn't say this very often. I really like to think of it in this way. What did we used to say about dividing by 0? Okay, we always say you can't do it. In algebra, you can't do it. Okay? Did we ever say sort of what the value would be? No, you can't do it. It would be called undefined. Okay, if you saw something over 0, undefined. You wrote it down, undefined. Okay? Now with calculus, you introduce something in between that. If you have 7 divided by 0, that's undefined. It's undefined in algebra, it's undefined in calculus. You can't do it. Okay? Now, that might be a change of 7 here, and if that were here, you'd be undefined because that'd be a vertical line. Okay. That's why you can't do that. Okay. But as you let this point get closer and closer and closer to the thing, your delta y is getting smaller too. And your delta x is getting smaller. So if your delta y over delta x, if that was 7 over 0, it's still undefined in calculus. But if that is going to 0 over 0, we no longer call that undefined, even though you're still dividing by 0. I call it indeterminate. Because which is going first? This delta 0 going faster than this 0 or what? That's what I call an indeterminate form. That's what calculus deals with, those indeterminate ratios. 7 over 0 is still undefined. 0 over 0 may or may not be undefined. It may be indeterminate. Now this book, this is old thinking, but to me that makes a lot of sense. So that secant line, as the second point gets closer and closer, as Q gets closer and closer to P, the slopes you can calculate and calculate until you get the delta x equals 0. At that point, it's no longer a secant line, it's a tangent line. If there is a limit there, then that has a limit, and that would be an undefined term. Okay. I'm sorry, not undefined, indeterminate. And calculus helps you determine. Okay? So the point P, C, F of C is the point of tangency, and Q, which is C plus delta x, comma, F of C plus delta x. Again, x, F of x, x, y. Okay, that's your Q point here. Is a second point on the graph, then the slope of the secant line through those 2 points can be found, and this is M of the secant line, SEC for secant, same as it was in trig. Okay, but we never refer to that what secant. F, this is your change of F, a change of x, change of y, because F of x is y. F of C plus delta x minus F of C, that's your change of y over your change of x, C plus delta x minus C. But look here, C minus C, that's 0. So you have change of y over change of x. Delta y over delta x, that's your slope of the secant line. It's just we do it in function notation rather than y notation. Okay? Now, as the point Q approaches that point P, the slopes of the secant line approach the slope of the tangent line, as shown in this figure. That slope is getting closer and closer. See, here's that first slope. Then as you get closer, it's getting closer to that tangent line. Even closer, even closer. Right down there, it would be very, very, very close. The limit of that slope as the delta x is approaching 0, that's going to be the slope of the tangent. And that's the limiting process, limiting position, would be where they're on top of each other. There, your delta x went to 0. Algebra, you couldn't do that. Calculus, you can. Do the limit as that delta x approaches 0. That's going to be your slope of your tangent line, if it exists. Okay? Now, we're not saying how. This is just this introductory, oh, think about this. Yeah. To me, it's not a complete waste of time, but we never, back in the old days, we didn't do all this. Yeah, okay. But let's look at another, the area problem. Second classic problem is the area under some curve. Not just the area under a straight line. I could even figure that out, okay? Either that straight line is going to form a trapezoid, okay? Yeah, I could do a trapezoid. Might be a triangle, you know. Could be anything. We know those regular patterns, okay? How are we going to do that if it's not? It's also solved by a limit process. But in this case, it's a little bit different, okay? It's applied to an area of a rectangle to find the area of a general graph. Whereas before it was a slope of a secant line approaching the slope of a tangent line, this time it's areas of rectangle approaching some other area. So here is the thing. Simple example, consider region bounded by this function, y is equal to f of x, okay? Now, to begin with, and this is pretty much what we're going to do, let's pick some region here from A to B where this f of x doesn't ever go negative, okay? Because if it went negative, you got problems. You got, now it's below the line here, but you're doing this. So let's keep the f of A and f of B are both positive, and f of x in between A and B stays positive always. Okay, we can do this. Simple example, consider the region bounded by that. I can't calculate that. Not now. Later you'll be able to. No way. I mean, because there's no, this is a variable boundary. This boundary's fine, that boundary's fine, this boundary's fine. This one, it's not very fine. So how do we do it? Again, approximate. Let's split that very same area into rectangles. And let's take the left-hand edge of this rectangle to be the height. Left-hand edge here to be the height. Left-hand edge here to be the height. Left-hand edge here to be the height. Well, obviously that's not going to be the same area, but it's going to be an approximation. This underestimates pretty big time. This underestimates some, overestimates just a little bit, so it's still a net underestimation. Here's a net overestimation, because it's always above that, but it's still not very much, especially compared to this, and here we really underestimated again. So it's not a very good estimate, but it is an estimate. So what do? Well, let's take these rectangles and let's do the, and by the way here, this A to B, we're now done into a delta x here, delta x here, delta x here, delta x here. And that would be B minus A, that would be the total length divided by 4, that would be your delta x here. Okay? This is not quite the same as the before, but you know, somewhat similar. Okay? Let's do twice as many intervals. So you have this. So you have 1, 2, 3, 4, 5, 6, 7, 8 now. Now let's look at the areas under this. Well, again, this underestimates, but not nearly as bad as this, because this next one covers a lot of this area that wasn't covered before. So now your underestimation is less. Here it's less than what it was there. Your overestimation is a little bit more. That was a little more. Underestimate that. You've improved your estimation of the area under this curve with the area under of those rectangles with the left-hand endpoints. Okay? Well, do you see where we can go with this? Let's keep getting our delta x to be smaller again. Let's do it in half again. Half. And using the same ones. Now we get a better estimate. And do it again. And again, until soon, if you have that delta x small enough, you almost are plotting that same curve. So guess what we do? Take the limit as that delta x goes to 0. Can't do that in algebra. You can do it in calculus once we know the limit. Okay? As you increase the number of rectangles, that's the decreasing the size of your delta x, the approximation tends to become better and better and better because the amount of area missed by the rectangles decreases and decreases. Your goal is to determine the limit of the sum of those areas of the rectangles as the number of rectangles increases without bound. As the delta x goes to 0, then your area would be approximating what you had there. Whoa, that was section 1.1. A pretty quick section. Didn't do any real calculations, did we? It was mostly just concepts. So homework exercises here. There is a concept check here, and most of the time we'll actually do these. This time I'm not sure it's really all that worthwhile. Describe the relationship between pre-calculus and calculus. You probably, I've said it over and over and over again. I think you probably have a pretty good clue on that. If not, go back and read it. List 3 pre-calculus concepts and the corresponding calculus counterparts. Let's go back. Look at the slides, you'll see. Secant and tangent lines. Discuss the relationship between secant line through a fixed point and the corresponding tangent line at that fixed point. And again, as the second point on the secant line gets closer and closer to that, you're approaching the slope of the tangent line. Now, here is the third thing about this text that I've never seen in any other book. Now, maybe you have. I haven't. Not even earlier editions that this author did. He just keeps getting better and better. Y'all recognize these things? It's some sort of a thing. Yes, exactly. Okay? This is a thing. In the old days, which was in my lifetime, we had barcodes. This is a rectangular barcode, basically. It just has a lot more little things in it. But your phone, or a lot of your phones, will probably read this. You could probably read that thing with your telephone, and it would probably take you straight to one of his websites. Okay? Wow. Now, I have my wife's old cell phone. I bet you it will do it, but I've never learned to do it. So I can't tell you how to do this. Y'all are young and savvy at this stuff. You can do it almost second nature like that. So if you learn it and see it and say, hey, you need to try this, you old man. Okay, I may or may not. Okay, so in these exercises, 3 or 5. 3, by the way, has a red letter by it. The digit 3 is red. That means calcview.com, this calcview.com, you can actually see exactly what they're looking for. At calcheck.com for any of the tutorial help and worked out solutions for the odd number exercises. I'm only ever going to give you odd number exercises. Okay? Okay. Now, so do either 3 or 5 in that first group. Do number 7 or 9 in the second group. And then if you want to do number 11 in that one remaining. In fact, I'd say 7 through 11. Do at least one of those. Okay? There's not much to do. It's just sort of generic. It's not really too much calculational. But if you can't do it, you can't get what they're looking for in the back of the book, then go to calcheck.com. Except for number 3, you can go to calcview.com and get even a better explanation. All right. Oh, man. I pulled a dumb one here. I'm going to have to run down to my office. The new edition of the book, the older editions of these texts always came with a DVD. You just plug it in and pull up. Well, the new one, I can only get the PowerPoint if I go to the publisher's webpage. Have y'all, yes? What's that? Absolutely. You want the ISBN? Anyone can do that if you want to while I'm going down and get it. So what I had to do, if you notice, the price of the books have really plummeted. They've gone down, right? No way. They keep climbing. And yet, what do they do with the resources they give us? They give us less and less and less. We have to go to the website and get the things. So they don't give us DVD. They don't give us, printed versions of test banks or anything else. I have to go to the website. So I've got to go down When I was first doing this, the only flash drive I had was this one, and it's almost full, so I didn't. I had to do the others on a different flash drive, and I didn't know we were getting the part today. So let me go and get that. I'll be right back. I will be back.
What time are you back? 11. 11:10. I thought we were going to be able to. It say 11 on the schedule.
You said 10:45.
Is it 10:45 on yours? Mine says 9:30 to
I need to copy that into this one so I don't ever have to do this again. But let me end this, and I think I have to end this. Okay, we got a few more minutes, folks. All right. Sorry, I didn't think we'd get this far. Well, I didn't know how simple the slides were. Okay. Okay, all that's loading. Did everybody get what they needed off my book? And you lost my page, didn't you? No, I didn't. Okay. Yeah. It's not hard to find. Okay, that was 1.1. Let's go to 1.2. All right. From current slide. I probably should have paused my recording so there wouldn't be all that dead time. But now I get to listen to what you said about me while I was gone. Okay, no, I'm just kidding. Okay, from current slide. Okay, still talking about limits and their properties. 1.2 is finding limits graphically and numerically. Boo hiss, okay? You can do them, but it takes a while. We'll estimate the limit using a numerical or graphical approaches. So notice the term estimate there, the word estimate. We'll learn different ways a limit can fail to exist, and we'll study the use of a formal definition of a limit. That's also a lot of fun. Okay, so introduction to limits. It says here, sketch the graph of this function. Okay, y'all know how to sketch graphs, right? Do a t-table or something like that. Give me some x's and plug in and get the alphabet, the y's, right? And plot them. Do you foresee any little problem that may arise here? What can you never do?
Zero at the bottom.
Ah, yes, as x is approaching 1, that thing's going snaky, okay? You can't do x equal 1. You can plug in any value in the world except x equal 1, because you can't calculate that for. But what form would that be, though? What would this be? X equal 1. Second? Indeterminate, very good. He picked up on it. 0 over 0. So don't tell me this one's undefined. In algebra it would have been, but in calculus we would call it indeterminate because you'd have a 0 over 0. Okay? but you still can't plot that on a graph, can you? Now, if you did plot, or some of you plugging into a graphing device, if you are, you can see it gives you a graph. The thing is, it just doesn't have a value of x equal 1. Okay? It can't. Okay? Now, so you could do that, and if you did do it, you are going to get a shape, and it'll look pretty familiar. It just will not have a value of x equal 1. Now, if you noticed when I said we're going to do this graphically and we're going to do it numerically, I went gag, okay, because those are both tedious, okay, in some ways. I'm going to show you another way to do this. I shouldn't do it yet because we aren't there yet, but I will. And it actually, to me, makes a lot of sense. Okay? Now, by the way, those who haven't been in my class before, remember I said everything that's projected on the board, which you see what's projected. Now, you notice my hand waving. That's not going to show up on the PowerPoint, on the YouTube videos. You won't see me at all. All you'll see is what's projected on the board. But I have an ionizing pen with this computer. This is a tablet computer. And I'm going to do something here. Now, if this was an algebra class, what would I be asking you to do first? Factor everything in sight. Now, that denominator is not factorable, is it? So it's going to say x minus 1. Is that numerator factorable? How? Say again? X what? Minus 1 times x plus 1. Is that what you said? Okay, is that what? Okay. Not quite. Not quite. Nope. Okay, I bet you somewhere back in your long past, you had a thing called the difference of two perfect cubes, didn't you? Oh, those were fun, weren't they? And we remembered them far past the next week, didn't we? Oh, sure we did. Okay. Okay. I'll review for you how I teach difference of two, sum or difference of two perfect cubes. Okay? It's going to be a linear term times a quadratic term. Not term, factor. Okay? The first one is going to be the cube root of these two entities with the same sign in between. So it starts off with a x minus 1, because the cube root of x squared is x. The cube root of 1 is 1. Keep the sign. Okay? Now, for that quadratic term, forget about everything else. This is just, it always works, so I use it. Square the first term. What's that? X squared. Okay, that was real hard, wasn't it? Now, opposite the product of the two terms. What's the product of the two terms? Product of x times minus 1. It's negative x. Well, you do the opposite of it, and it becomes a positive x. Okay? And then square the last term. Is what? Plus 1. Now, if you don't believe me, you can multiply these out and see. X times x squared is x cubed. X times x would be x squared, but minus 1 times x squared would be minus x squared. Those add to 0. X times 1 would be x. Minus 1 times x would be negative x. Those add to 0. And minus 1 times plus 1 would be minus 1. Sure enough, that works. Okay? Now what can you do, folks? Yes, you can divide out the x plus 1, x minus 1s. And this gives you a shape. If you had graphed it on the graphing calculator or had done it by hand, that would give you a parabola. Okay? A funky kind of parabola, but it would be a parabola. Now, in this form, this, we would say in algebra was equal to that. But in the function, it's not, because this you can plug in a 1 there, couldn't you? 1 plus 1 plus 1, that would be 3. But you can't do it here. So you still have to have a hole in your graph there. Everywhere else, that's a parabola. Every other value you plug in there will give you the same value if you plug that in here. Just x equal 1 you couldn't do. That would give you a hole in the graph. Okay? So that's what they're going to do, is show you that. Well, they're first going to do it numerically. Okay? Now, we're out of time, aren't we? We'll start next time with this. We'll do this slide right here. It'll be gory. Bring your calculators next time. Phones will be fine. I don't care. Just anything you can do your calculations on. And we'll investigate this. Okay? All right. Good deal. Did we get far enough in this for any new exercises? Probably not. So we'll go. Now, the other time, if you recall last time, and not all of you were here, I said bring with you, and at the time I said this week or next, and next week we didn't even meet. Be thinking about a paper topic, and if you can come up with at least a preliminary idea of what you would like to write on, go through the book, go through, like, in just a page or two, we're going to hit a guy named Peter Gustav Dirichlet, I think is how you pronounce his name. German, sounds like a French name, but Gustav is very German sounding. He was a German mathematician. He would be a potential paper. You don't have to write on people, but I'm just saying, there's all these things through your book. Look at them or think through things. What would I like to do in this, Come up with some paper topics either next time or next week, because I want you to start thinking of these things now, because better start on the paper now than wait till the end of the term. Okay? Good deal. Good class. We'll see you on Wednesday. I sure hope we'll see you on Wednesday. Okay.